My name is Rebecca Matasotsky. I'm an associate editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information to ASHRAE Journal readers and to others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by SimScale. The subject is Simulate Ventilation Equipment and Strategies using Cloud-Native CFD. Today's speakers are Ajit Kumar and Richard Suker-Schuler. Ajit Kumar is an application engineer. He has a background in aeronautical, aerospace engineering, and a master's degree in computational engineering from Ruhr University, Bochum. Richard Suker-Schuler is SimScale's product manager. He has a background in applied mathematics and mechanical engineering. Richard, the microphone is all yours.
Thank you for the nice introduction, Rebecca. And thanks to ASHRAE for hosting today's webinar. Hello, everyone, and welcome to today's webinar about simulation of ventilation equipment and strategies using cloud-native CFD. My name is Richard Suker-Schuler, and I'm product manager here at SimScale for the AEC applications, so everything regarding architecture, engineering, and construction. And today with me is our senior application engineer for AEC topics, Ajit Kumar, and he will later in the webinar show you a case study and a live demo of the SimScale platform. Before we start with the webinar, I would like to encourage everyone to use the Q&A functionality here and post a question whenever a question comes up to you, and we will spare 10 to 15 minutes towards the end of the webinar and try to answer all of your questions. So I'm really glad that we have so many attendees today on today's topic on mixed mode ventilation using CFD in the cloud. Before we start with the actual topic, I would take a step back and quickly introduce to the ones of you who haven't heard about SimScale yet, what SimScale is, what we do, and what makes us different from traditional CAE providers. So our motto here at SimScale is we want designers and engineers to simulate early, simulate more, and most importantly, start simulation now. SimScale makes high fidelity engineering simulation technically and economically accessible at any scale and in the cloud. As of today, we have already more than 300,000 users worldwide that trust SimScale's ability to model multiphysics simulations accurately using cloud-based technology. So what sets SimScale apart from traditional CAE providers? We have seen three main barriers in the CAE industry that keeps people from actually using simulation technology to its full potential. First of all, on the left side, traditional CFD usually requires high performance computing capacity to be able to perform high fidelity simulation. So there's a high hardware cost initially before even getting any value out of simulation. With SimScale, we're a cloud-based simulation tool. There's zero hardware footprint and zero software footprint. It means you don't need to buy any additional hardware or install any software on your computer. You can simply start simulation with your local laptop by going to simscale.com and signing up. Traditional CAE tools are have a high fixed cost initially, while SimScale has a cost-efficient software as a service offering. So there's no fixed expenses for hardware and a flexible usage-based pricing. Most importantly, in traditional CAE tools, there's usually a high know-how barrier, as the tools were specifically designed already decades ago for engineers that have a special education in the field and still need training to really perform simulation with traditional CAE tools. With SimScale, we from the beginning focused on ease of use of the tool. From the beginning, we envisioned SimScale to be a tool to be used by engineers and also by designers efficiently. While focusing on the user experience, additionally, what SimScale offers being cloud-based, is a seamless collaboration environment. So simulations and setups can be shared between colleagues, and so the knowledge and know-how can be shared as well. And additionally, SimScale provides in-tool live support. We see that later with the presentation of Ajit. Within SimScale, within the tool, you can directly at any time have access to one of our application engineers and ask any questions you might have regarding the simulation setup, regarding evaluation of your results and interpretation, and have your answer right away. So now let's take a look at today's application. Today we want to focus on a case study on mixed mode ventilation in buildings. We will show how we can predict wind and buoyancy driven air movement within the room, how to assess air quality, and also how we can calculate fresh air rates and CO2 concentration within the rooms. We will focus on the insights into the performance of mixed mode ventilation strategies by modeling accurately the spaces, occupants, and equipment using a 3D CAD model. Before we go into the actual case study, we want to show in general how SimScale is used to optimize airflow performance of ventilation products and HVAC units with engineering simulation. We will show then the live demonstration and have the Q&A at the end. Additionally, we'll show you how you can quickly get started with SimScale. Now, let's see which types of HVAC products we can analyze using SimScale. There's a variety of different types of HVAC equipment that needs or could benefit from doing CFD analysis. One example is on the top left, an HVAC unit designed by one of our customers, Monodraft. And they designed and developed a net zero hybrid ventilation system called the HVR0. And it provides a natural ventilation hybrid, mixing ventilation and low energy mechanical heat recovery in one compact unit. And with SimScale, they could optimize the air paths within the unit to increase the ventilation flow rates and reduce the fan power consumption by 50%. Additionally, one component that always is important is the ducting design itself, typically calculated by simple measures. With SimScale and CFD, you can have accurate pressure drops across a complex system of ducting designs. On the top right, we see a micro louver fabric. This is designed by one of our customers, Smart Louver. And their product micro louver is a woven mesh of paper-thin louvers, and it's used to enhance the performance of any glazing or building facade. And they use SimScale to analyze the discharge coefficient of different configurations of the micro louver design. And with this discharge coefficient that they have gotten from SimScale, they could be input directly into thermal modeling tools such as IES, TAS, or Design Builder for further thermal modeling. Additionally, they analyzed the solar shading characteristics of their micro louver product with SimScale. Additionally, components that often play a role and need to be optimized in a specific configuration are diffusers, air inlets into the rooms, or complete air handling units, which we see on the bottom right. They have different components, cooling components, heating components, performance for filtration, and so on. And all of these together make up for the total behavior of the air handling units. So with SimScale, you can either analyze specific subcomponents of it, but also analyze the complete air handling units together to see how different design configurations, orderings, louver angles have an effect on the complete unit performance. And obviously, smaller components, supply fans as well, can be analyzed with SimScale to get the characteristic performance curves of these as well. So each individual component can be analyzed separately, but then as well, interesting in the end for the occupants in the building and the owners is the performance of all of these systems together. This can be also done with SimScale to actually analyze the performance of these components in the complete design of the room or in the building itself under various outdoor and indoor conditions, occupant conditions, or additional heating devices within the room. Finally, a case study from our customer Silent Air. And they are designing and engineering and also manufacturing cooling and modular data center solutions. So Silent Air needed to validate the mixing performance of their air handling unit. And in this case, it was critical to ensure that no parts of the downstream airflow should vary by more than 0.8 degree versus the average supply air. Because in this case, a part of the airflow was diverted and bypassing in an evaporative cooling system within the unit itself. It was critical to ensure that the airflow outside of the unit was pretty well mixed. And an analysis was set up to match a real factory witness test with the first prototype that had 24 temperature sensors installed. And with SimScale, it was possible for them to validate that this air handling unit performance was good enough and give them the confidence that they can start building the actual 320 units that were required by the end customer. Also, Silent Air modeled several different internal design layouts to see which of the different layouts would yield the optimum mixing performance. And all in all, Silent Air could reduce the overall pre-testing phase from 4 to 6 weeks to, in this case, 2 to 3 weeks. So they reduced the overall development cost, in this case, by 50%. And here we have a very encouraging quote from Shane McConn, the lead mechanical design engineer at Silent Air, who said, "Months of engineering work can now be done in an evening." So that's maybe a little bit optimistic, but it's a true statement of one of our customers, which really sees the potential and the benefit of using simulation, especially cloud-based simulation, where you can analyze multiple different designs in a basically parallel form all at the same time. So with this, I'll hand now over to my colleague Ajit, who will show you now live demo of the platform and introduce you to the functionality and the case of today's webinar of the mixed mode ventilation.
Thanks, Richard, for the brief overview of how a cloud-native simulation tool can help formalizing a ventilation strategy. To understand better how an early-stage design or simulation can help us devise the ventilation strategy, we're going to take a look at a case study on this purpose. Before moving ahead, I'll remind all the audience to actually make use of the questions section and ask any questions that comes to your mind. We do have Richard, who is our product manager, so he'll be happy to actually answer some of the product-related questions when we complete this technical case study demonstration. Let's take a quick look at the case study itself. So for this particular case study, we have a classroom with a certain number of occupants present inside. There are certain challenges that we need to address to make the design optimal by keeping in mind certain requirements given by the design team. So on the left-hand side, you can see the base configuration. As I mentioned, we do have a certain number of occupants, which includes both the students and the staff members. Other components like windows and HVAC inlets and outlets are also considered to make the simulation close to reality. Let's take a look at what the base configuration provides at the existing level and what are the challenges that we need to address to make the ventilation strategy optimal. So there are two major issues in the base configuration. The first one is the indoor space, which is considered here, is subjected to higher levels of CO2 concentrations. This affects the quality of the air inside this particular classroom. The next issue that is projected here is the uneven temperature distribution, which is also caused by the stack effect. The challenges here are to improve the air quality and also tackle the temperature distribution issue. There are also certain restrictions that we need to consider while doing optimizations, such as the thermal comfort of the occupants. So the base case has a good thermal comfort parameter for the occupants, but moving forward, when we make design changes, we need to make sure we either maintain the same level of thermal comfort or by any chance increase the thermal comfort of the occupants. We're also given with certain parameters that we can play with for the optimization of the ventilation. The first one is the HVAC sizing. Obviously, if you have a temperature issue or if you have a higher concentration level, the first thing that comes to our mind is to increase the flow rate. So this talks about the HVAC sizing, and in the coming slides we can see how the change in inlet flow rate or the HVAC components can affect these parameters for quality and thermal comfort. We can also play a little bit with the ventilation strategies. What it means is that we can use the forced ventilation to tackle these challenges, or use a mixed or a combination of forced and natural ventilation to tackle a particular scenario. Before getting into the actual optimization loop, we can take a look at the ventilation requirements as we mentioned before. There are two major requirements that we need to satisfy moving ahead with the optimization. The first one is the quality of the air. And why is it such an important factor when it comes to indoor spaces? This can be explained by the quality norms which is provided by DIN, which actually talks about the levels of concentration of CO2 inside the room and how that actually affects the occupants present inside. For example, for an indoor space with good air quality, we need the concentration levels between 400 to 1000 ppm, with 400 being the general or common levels of carbon dioxide in the ambient air. And as the levels of concentration increases, there are certain adverse effects that the occupants might actually experience, such as headaches or even brain damage in some cases where the higher concentration levels are present. So we need to consider these restrictions and try to optimize our ventilation strategy that comes with these norms. And on the right side, you can actually see the restrictions for the thermal comfort. And this is also defined by certain other standards like ASTRAE 55 or ISO 7730, where we have certain thermal comfort parameters like PMV, which is the predicted mean vote, and PPD, which is the percentage of person dissatisfied. So for a good thermal comfort, we need to make sure these values are between minus 0.5 to plus 0.5, which particularly means that the temperature inside the room should not affect the occupants in a colder way, or it should not be more warmer for the occupants. With all these requirements and considerations, we'll move ahead and see what are the configuration changes we can do to make sure our ventilation strategy is cost efficient and also comes under these particular standards or norms. Once again, we have the base case, which you can consider as an existing building which we need to modify or optimize. So from the base case, we have certain parameters like the HVAC inlets and outlets, and also ventilation strategies that can be a combination of forced or natural ventilation. So as a first optimization, we're looking at the configuration 1, where the HVAC inlet or the supply inlets are optimized to get a good level of airflow or air exchange rates within this indoor space. So for configuration 1, we're going to play with the inlet flow rates and also the angle at which the diffusers are present at the inlet. This can be considered as a sub-optimization where we are focusing only on the HVAC supply unit. And once when we find an optimal level of HVAC inlets and the diffuser angles, we can actually check the next configuration, which is again a combination of forced ventilation, which is optimized for flow rate, and the diffuser angles. In addition to that, we are going to actually open the windows of this classroom. So the windows considered here are top hung and open only at the bottom. So we can take a look at different combinations of these configurations and find out which one better suits for this indoor space. Once again, before moving on to the next section of this webinar, which is a technical presentation, which I'm going to actually perform live over SimScale, where we can actually take a look at how we can approach the simulation setup with the available parameters and how we can arrive at the results which might be optimal for this particular indoor space. So please feel free to use the question section and ask your questions so that we can discuss that at the end of this technical presentation. For the live demonstration, we'll take a look at SimScale platform and then check how we can set up these kind of simulations and analyze the results afterwards. Within SimScale, there are three major steps before you start the simulation, starting from importing your 3D geometry, setting up your simulation, which includes the boundary conditions or the inlets and outlets of the HVAC system, the heat sources, the concentration sources, and anything else that affects the physics of this particular simulation. Once when these two steps are done, you can start the simulation and analyze the results. For those who are not familiar with SimScale, SimScale is a cloud-native simulation tool. And what that means is you can access high-fidelity simulation by using a simple browser and an internet setup. As you can see here, within the browser, you can access SimScale by clicking on to simscale.com, just like any other website that can be opened on a browser. Once when you are inside simscale.com, you can log in to your own account and then get access to your dashboard. The dashboard is where all your projects are stored or displayed. From this point on, you can create a new simulation from scratch or open an existing project and start modifying the simulations. We'll take a look at the ventilation project that we talked about, and this is how the simulation setup actually looks like. The workbench has certain sections where we can actually focus on setting up the simulation or actually analyzing the results. For example, you can see on the left side the geometry list and also the simulation list. On the right side, you have the geometrical entities which can be accessed by clicking on them, or using the viewer, you can click on them to access it independently. To start with any kind of simulation, you need to upload the 3D geometry or the 3D CAD model. This can be done by clicking the geometry option and simply dragging and dropping your geometry inside this dialog box. SimScale supports quite a variety of native formats from SolidWorks, Autodesk Inventor, Rhino, CATIA, and any other tool that is available in the market. You can also use generic formats like STEP, IGES, or STL, for example. Once when the geometry is imported into SimScale, you can take a look at the geometry from the geometry list. For this particular case, we are going ahead with the base configuration. Within SimScale, you also have the options to modify your geometry in case of any cleanup required. For example, if you have an unnecessary component inside your CAD geometry and you would like to remove it, you can do that within the CAD mode. For now, we'll go ahead and start a simulation. And this is where you select the analysis type that you would like to simulate. For our particular case, we need a fluid volume, and the heat transfer should be considered to accommodate the HVAC system inside your simulation. Apart from that, you can also do a simple fluid simulation using the incompressible flow, or according to your requirements, you can also do other types of simulations under the same hood. You also have the access to run certain amount of structural analysis in case if you want to do a load bearing test or any other structural analysis. For this particular case, we'll go ahead and select the convective heat transfer and create the simulation tree. Let's take a look at a general overview of how the simulation setup looks like, and then jump on to one of the preset simulation to give you deeper insights on how the boundary conditions are set. So starting from scratch, the simulation tree looks like this, and this will guide you through the simulation setup. All you need to do is simply follow the top-down approach and set up all these red circles to make sure they are set properly before you start the simulation. This basically consists of three main steps. The first one is to set the materials. The second one is to set your boundary conditions. This is where you can actually set the inlets and outlets, any temperature conditions or any source conditions. Once the boundary conditions are set, you can simply go ahead and start the simulation right away. Let's jump on to the base configurations and check what conditions do we have for this particular scenario. For this case, we have the convective heat transfer analysis, and we have set air as our fluid medium. Select one of the materials from the library, or even create a custom material by simply changing the parameters on top of it. Once when the material properties are set, you can go ahead and select the volume, which is considered as the fluid medium for your simulation. Delete the additional ones and take a look at the materials assignment here. So we have selected the entire room and stated that this room is full of air. The next important step is to set the boundary conditions, and this is where you set up all the HVAC inlets and outlets or any other temperature conditions. For this particular case, we have a set of outlets at a particular flow rate, and we do have a set of supply inlets. We have other conditions like the heat transfer conditions that is going to happen on the walls and the surfaces of the windows here. This can be set using a heat transfer coefficient, and also set any insulation parameters using the wall thermal conditions. One other important boundary condition is to set the occupant thermal conditions. What this means is that we have certain amount of occupants within the system, and we would like to consider them as a heat emitting source. If you hide this face, you can see the occupants, and by selecting the external faces of the occupants, you can apply a particular heat flux for them, so that this acts as a heat source within this indoor space. This is all about the boundary conditions. You can go ahead and take a look at the other conditions which might be helpful for this condition, for this simulation. But once when the boundary conditions are set, you're almost ready to start a simulation. This can be done by clicking on the simulation runs, and this will give you a rough estimate of how much time the simulation is going to take and the computational resources. Since we are on cloud, you can take leverage of certain other possibilities within SimScale. For a traditional CFD tool, when you start a simulation, you might need to block the computer for the simulation to run through, and then you can use the computer afterwards. But since we're on cloud, you don't need to wait for any simulations to finish. You have the capability to run multiple simulations at the same time in parallel. For example, if you have a different boundary condition that you would need to check, then you can go ahead and select the particular boundary condition. For example, we select the walls, or we select the occupancy, and then instead of the heat flux value here, you can go ahead and change that particular value, save this particular boundary condition, and start a new simulation with the new configuration. This is how a general setup within SimScale looks like for such a ventilation case study. Moving forward, we have two different configurations that needs to be simulated and compared with. To do that, you can check the geometry or import the other configurations in the same project. For example, we have the configuration 1 with a varied HVAC supply and configuration 2 with open windows. So we can import multiple geometries into the same project, and from this point on you can simply use the geometry and set up the simulation for the particular configuration. Instead of starting everything from the beginning, you can also use your base configuration where you have already set up the simulation. For example, you can take the base configuration you're confident with, duplicate the entire setup, and now all you need to do is swap the geometry for your different configuration. Right now we have selected the configuration 1 as the geometry for simulation, and this will generally preserve most of your boundary condition based on a named phase tag. For example, while importing these geometries, I've also created a bunch of topological entity sets in the CAD tool. So while you're importing, these CAD phase selections are preserved within your geometry. This will help in actually setting up these different configurations easily. For this case, since we have swapped the base configuration with the configuration 1, you can already see most of the common or similar boundary conditions are preserved, and all you need to do is go ahead and change the additional modifications that you have done. For this case, we have changed the supply inlets, and go ahead and start a simulation right away. This way you can actually run multiple configurations at the same time within a less amount of time for the simulation setup. This can be repetitive, so you can also take one of your configuration 1, duplicate, go to the geometry and change it to configuration 2 with open windows, and here you can see as well most of the boundary conditions are preserved, and in addition we would need to add the inlet from the window. So we go ahead and create a new boundary condition as velocity inlet, select the faces that are going to act as an inlet through the window, set the boundary conditions here. For example, you can set a component velocity for this particular case. Set the temperature to be a little bit higher since we are comparing the summer scenario here. Save this and start the configuration 2 as well. So right now we have all the three configurations running in parallel, and by the end of certain amount of time you can come back and take a look at the results. As the simulations are running, let's take a look at one of the pre-run simulation. For example, we'll go for the base configuration and click on the finished run, where we can access the post-processing section of SimScale. In this particular case, we have created a slice of the 3D domain, and when the result loads, you can see the distribution of temperature over that particular cutting plane or the results section. So there we go. We have a cutting plane or a slice at 0.85 meters, which is at the sitting level of the occupants, and we have plotted the temperature for this particular case. If you're really interested in certain points within your domain, you can also inspect the points and see what is the temperature at this particular location. In case of comparison, you can also use the result statistics and get an average, minimum and maximum temperature or the velocity values on this particular cutting plane. For example, here we have an average of about 23 degrees Celsius on this cutting plane. You have several other options like streamlines, isosurface and isovolume, which can be used to deduce insightful results from the simulation. Let's take a quick look at the comparison between the configurations. I have already extracted the results from all these three configurations and put together in this slide deck. So let's quickly jump back to the slide deck and discuss about the results in detail. At this point, I'll again remind the audience to actually write your questions in the questions section so that we can discuss at the end of this presentation. The first results we are interested in is the distribution of the air within this room. So comparison between the base configurations and the other two configurations are done here. On the left, using the base configuration, you can already see that due to the lesser HVAC inlet, the air tends to move downwards right from the inlet due to the ambient conditions present within this room. And this is optimized by increasing the HVAC sizing and also the diffuser angles of the inlet here. So here in the configuration 1, you can clearly see an upward draft from the inlet, and this generates a huge recirculation which helps in distributing the air all through the indoor space. Again, on the configuration 2, in addition to the upward draft, we also have the windows open, and here you can see the interaction between the air coming from the window and the fresh air coming from the HVAC supply. And what this air distribution creates with respect to the temperature and the air quality within the room. This can be seen in the next slides. So taking a look at the temperature distribution, with the base case, there is a dominant stack effect happening. Just because the inlet velocity is low, the HVAC inlet tends to move down, and this creates an upward convection of the temperature within the room. The stack effect here can be clearly seen and is dominant. And to avoid this or optimize the temperature distribution, the HVAC inlet flow rate is increased, and this will generally tend to create a better mixing of the temperature within the room. This will help distributing the temperature from the heat sources, which are the occupants, and this recirculation will help in better removal of heat from the occupants. Once again, with configuration 2, the combination of the open window and the HVAC inlets helps increasing the better mixing of the temperature. The next slide will give you a clear idea about how this temperature distribution affects the thermal comfort of the occupants. Here on the left, for the base case, you can already see the occupants are in yellow color, and what that means is, according to the predicted mean vote scale, anything above 0 is warmer for the occupants. So the yellow color symbolizes around 0.8 to 1 for the predicted mean vote, which means the occupants are feeling a little bit warmer than required. And this is a little bit optimized for configuration 1 and 2, where you can already see the occupants are in green, which means they are near the neutral region of the thermal comfort parameters. Once again, if you remember, all these optimizations are done keeping in mind that the thermal comfort is not affected much. So here we can see a marginal change in the thermal comfort, but on the good side, I mean, the thermal comfort has been increased when we have changed the inlet velocity of the HVAC system, and also by opening the windows during the summertime. This will help keeping the occupants thermally comfortable. In the next slide, we can see how the air quality changes within the system. So as in the base case, due to this stack effect, there is a high dominant upward rising air, and this creates a large amount of concentration near the ceiling, and there is no better mixing in the room with the air quality. So you can also take a look at the amount of CO2 at a particular level in the next slide, but comparing these three designs, you can already see that configuration 1 and configuration 2 has better mixing of air, and the fresh air that is coming to the HVAC supply takes away most of the concentration near the occupants and tries to put that to the outlet or through the window. here is a good comparison between the air quality at the sitting level of the occupants. So as we have already discussed, we have the base case where the concentrations are quite higher near the corners, and also as an average, we have higher concentration levels of CO2 at the sitting level. And by using configuration 1 and 2, we have drastically reduced the amount of concentration within this room. What's good if we don't actually see the amount of numbers, or what is the percentage of reduction in CO2 level. So when compared to the base case, the configuration 1 is about 18% better in removal of CO2 from the room. And from configuration 1 and 2, you can already see a 4% increase in the removal of CO2. This means the configuration 2 with open windows and with the optimized HVAC inlet performs better in this particular scenario. So this way you can actually compare different designs by running simulations at the early stage, so that this will help you size the HVAC units better, and also make sure that the thermal comfort is actually maintained inside this indoor space. This is all about the kind of results. I hope this gave you a clear idea about how simulation can help you predict a good ventilation strategy, and I'll leave the stage for discussions now.
Thanks, Ajit, for the great presentation of this use case. And yeah, so I think we have really seen now how SimScale can be used efficiently to model different scenarios, to run different design changes efficiently, and compare them against different design criteria. So we have seen that with Cloud Simulation Tool, we can optimize the HVAC supply required for a specific space under the specific conditions. We can improve the thermal comfort for the occupants based on different ventilation strategies, and also the air quality can be optimized with different strategies and can be evaluated with SimScale qualitatively, but also quantitatively. So now the last part, we have about 15 minutes left for our Q&A session, and I'm glad that we have so many questions that we should better start now with them. I'll start with the first, and then I'll hand over to Ajit. The question was, what tools do you normally use to provide the 3D model? So as Ajit has shown in the demo, we enable a variety of different CAD formats that can be uploaded to SimScale. In the ASD industry, typically Rhino, Revit, but also STEP are common file formats, but we usually can support all of the industry standard file formats.
Thanks, Richard. So let me take the next question. So it's an interesting question. So natural ventilation amount can be affected by the amount of wind and its direction. So that's an interesting point. So for this particular model, what we did is we took the external wind conditions, and obviously we took an average value of the wind that could actually enter the windows and supplied that as an input for the internal case study. So that's the approach we took to make sure we are considering the change in wind direction and changing wind conditions on the external side.
Yes, one comment on this on top. So with SimScale, we have the ability not only model the inside of the building, but also the external surroundings. For this, we would use a different solver, which is a lattice-Boltzmann-based solver called Pacefish. And with it, we can analyze all different, up to 36 wind directions for a typical year. And based on these results, we can get the pressure coefficients on the different window openings. And then we can use the pressures from this simulation and put in here as a boundary condition, alternatively, for the indoor CFD analysis. We have another case study on our website, which you can have a look at, where exactly this strategy was used.
Yeah, thanks, Richard, for the clarification. And there were several questions about acceptance of Autodesk Revit. But as my colleague Richard mentioned, if we can write out the Revit family file, and then you can directly import into SimScale. There are other options like writing out as an STL or a SAT file that will be supported by SimScale for this kind of modeling.
Thanks, Ajit. There's another question regarding what's the difference between incompressible and incompressible LBM. So these are two different solver technologies that are underlying. The incompressible LBM solver, as said, is powered by Pacefish, which is a lattice-Boltzmann solver that is isothermal and is used for outdoor external flow cases around buildings. So we want to have a large-scale analysis on the building and its surroundings. That's where we use the incompressible LBM solver. The incompressible solver itself is used more on internal flow cases and is based on a derivation of the OpenFOAM solver.
Okay, there are several questions about importing the geometry and how we can actually make use of changes in the geometry. So as I mentioned in the live demonstration, if you have a CAD tool which can actually allow you to provide a named tag for all these surfaces, then you can actually tag them according to your inputs and then bring it into SimScale, which will be again recognized for your boundary condition setup. And this will help a lot if you have like slight changes in your geometry, but you have to run like multiple simulations for different configurations.
Thanks, Ajit. There are several questions regarding the accuracy of the solvers we use and studies between SimScale and maybe competitors like what's here mentioned, ANSYS Fluent. Yes, so we have on our website as well, as a part of the documentation, a section regarding validation cases, where you can have a look. We compare against different tools. It's a variety of tools. If you want on your own to also validate SimScale against one of your cases, we're happy to support you on that. We're confident that we're solving the same equations as other competitors, and will also get accurate results within the limits of a modeling tool.
Thanks, Richard. There is another question on how to check the mesh quality. So that's again an interesting question. So within SimScale, as Richard mentioned, the main vision here is to make sure the tool is easy to use. And even if you don't have expertise in meshing or setting up a simulation, SimScale actually guides you with automated solutions on that. So that's why you have automated algorithms that is working in the background that will mesh according to your imported geometry. And if you're really interested in checking the quality, we do write out a lot of mesh quality parameters that you can take from the meshing log.
Exactly. On top of that, we have a mesh quality viewer. So you can investigate the mesh quality on a cell-by-cell level and investigate the typical mesh quality metrics also in the post-processor with that.
Thanks, Richard. Let me get through some of the questions.
Yeah, the question was regarding if the simulation was steady state that we shown you. Yes, this was a steady state analysis. That's a quick one.
Yeah, thanks. And there's also a question about exporting the kind of simulations for third-party post-processing. So most of the simulations that you do within SimScale can be post-processed in the online post-processor. So we do have a lot of filters which is available for post-processing. But in case if you would like to use a third-party tool like ParaView, you'll be able to download the results directly and open them with the third-party tools.
Thanks, Ajit. There were several questions regarding building orientation with respect to sun and if you can take into account solar radiation. Yes, we can. We just yesterday had another webinar specifically about solar radiation. So if you're interested, you can check it out on our website as well. So to make it short, we can also include solar radiation. We have a solar load functionality where you can input the coordinates of the building, the north direction, and the time and date. And this will be taken then to actually put the solar rays in the right direction. And we have then the ability to put semi-transparent windows with specific emissivity and transparency. And then you will have the account of the solar radiation taken into account in the heat gain inside the building.
Thanks, Richard. There's another question on what are the preferred browsers to use SimScale. So we generally recommend using Google Chrome or Mozilla Firefox for most of the compatibility, but SimScale should also work on Safari on Mac and other browsers as well.
Thanks, Ajit. There are several questions regarding interoperability with third-party tools like Trace 3D Plus, also building energy modeling tools, and so on. So SimScale has an API connection. With that, you can basically write any scripts, connect with any third-party tool that also has scripting functionality, and integrate that with your workflow together with SimScale. So this can be used to set up complete analysis workflows, download results, post-process it, take automatic screenshots, and so forth. We don't have a lot of pre-baked plugins yet. We have functionality available through some of our customers with SketchUp, with Rhino, and yeah, several others are coming. But in a general form, you can integrate with any other tool that has scripting capabilities via the SimScale API.
Thanks, Richard. There's also a question about this particular case study. So whether the heat generated by the occupants were included. And the answer is yes. We did actually include the heat generation for every occupant. And this also accounts for the temperature changes within the indoor space.
Thanks. Then there's a question regarding what we can extract from the results, if you can get any statistics of specific areas of interest or an entire plane. Yes, that's possible. We have a, it's called, I think, bulk calculator on the post processor, where you can select a specific surface and it gives you statistical quantities like the min, max, average value of a specific field on the surface, and also integrates the surface integral quantities on the surface, and it can be also used on cutting planes.
There's also a question on how do we calculate the thermal comfort parameters. So that's interesting because within SimScale, when you're running the simulation, you'll be able to actually set the metabolic rate, the clothing coefficient, and the relative humidity, so that this accounts for the calculation of thermal comfort parameters.
Then a question on the heat load on the occupants. Ajit, did you use a surface or a volume heat load?
For this particular case, we use the surface-based heat loads.
Then there's a question regarding the geometry from other software if we have to introduce the wall thickness. So we have different modules in SimScale. What we've seen here today was the convective heat transfer analysis, where we start with the fluid volume only. We have a conjugate heat transfer analysis as well, where you can bring in the fluid and also the walls and other structural parts. Also in the convective heat transfer analysis, you can, on the boundary condition level, put the specific thermal properties of the facade in as well, meaning the heat transfer coefficient, the thickness of the facade, and the external conditions out in the outside environment as well. So with simple constant thickness facade elements, you should be able to model that accurately also with the just the convective heat transfer analysis.
Thanks, Richard. There is a question about the size limits of the domain modeled and the number of cells. So I think I can break that question into two. Regarding the size limits, there is no particular limit on what kind of domain you can actually model. For this case, we just modeled a classroom setup, but you can also bring in multi-storied building for these kind of analysis. So there is no particular limit on the size of the models. And the next question, number of cells. If I'm not wrong, this is about the number of cells in the mesh. And again, since we are using the cloud computing, you can also bring in complex models. And even if you have high number of mesh density, you can actually choose up to 96 cores of machine per simulation that you start. And this will compensate on the runtime and the number of cells in the domain.
Great. One other question was regarding the mesh controls. We have quickly touched it already. So in general, the meshing approach on SimScale is we try to automate it as much as possible, and we do a physics-based meshing. So if you follow the steps as shown by Ajit, you start to first set up the physical problem, and then you just start a simulation, which in the first step will compute the mesh. And the mesh computation algorithm will take all the information that is available from the simulation setup and automatically adjust the mesh behavior in an optimal way in general. So if there's a wall, it will assign layers to it. On faces which act as an inlet, there won't be a layer on it, but it will have a more refined mesh towards the inside of the domain, because we can expect some inflow in that direction. So in that sense, we already try to have a more or less optimized mesh as a default setting based on your physics. But of course, if you want, you can have also manual control over local refinement levels, addition of layers, the number of layers, the thickness of layers, local refinements on surfaces or in volumes. That's as well possible if you like to do it on your own and take on the control here. So Ajit, one last question for you, and then I think we have to close it for today.
Sure. There's a lot of questions about like how can we access SimScale, and what are the plans that are available. So we encourage you to actually go into simscale.com, where you can contact us using the email IDs here, and we'll be happy to actually sit with you and discuss about your projects or how you can actually gain the professional account for your projects here.
Yeah, thanks, Ajit. Thanks again for all the participants today. It was really great to have so many interested people in today's webinar, and we see that on the amount of questions we get. It was really a pleasure having the webinar today. Also, thanks to Ashra. And I hope see you again next time in one of our webinars. And with that, have a good day, have a good evening, and see you next time. Bye.
See you next time. Bye.